Hello everyone, today we're going to talk about data transformation techniques. My name is Mauricio and together with my colleague Anderson, we'll walk you through some of the most common ways to prepare data before training a machine learning model or algorithm. So first, why do we even need to transform the data? The short answer is that raw data is almost never ready to use directly. Before we can train any model, data needs to go through collection, clean, and transformation. The big reason for this is that many machine learning algorithms are sensitive to size of the numbers. If one feature goes from 0 to 1 and another goes from 0 to a million, the model gets confused. Transformation brings everything onto a common scale without changing the actual relationships in the data. Let's start with normalization, also called min-max scaling. The idea is simple. We can rescale all values so they fall between 0 and 1. The formula is x prime equals x minus the minimum x divided by the maximum x minus the minimum x. So the smallest value becomes 0, the largest becomes 1, and everything else lands somewhere in between. But there's one important thing to watch out for. Normalization is very sensitive to outliers. If you have one extreme value, it compresses all the other data into a tiny range. That's why you should always handle outliers before applying this technique. Now let me show you how this looks in the code. Here we can start by importing NumPy and 3 scalars from a library called scikit-learn. These scalars are of course going to let us execute the transformation techniques. Then we define our data, the values 100, 200, 1000, and 5000. We then reshape it so it has one column. That's because it's the format the library expects. Here we create a min-max scalar and call fit transform on our data. That line does everything. It finds the min and the max and then rescales all the values. Looking at the output, 100 becomes 0 or minimum, 5000 becomes 1 or maximum, 200 becomes about 0.02 and 1000 becomes about 0.18. You can already see the outlier effect here. Because 5000 is so far from the other numbers, the values 100, 200, and 1000 all get squished down near 0.
Now I will explain standardization, also known as C-score scaling. Standardization is transforming data so it has a mean of 0 and a standard deviation of 1. To do this, we subtract the mean from each value and divide it by the standard deviation. The result tells how far a value is from the mean, so values above the mean become positive and values below the mean become negative. One important advantage is that it handles outliers much better than normalization, because it is not based only on extreme values, however, it is still affected by them. And finally, it is important to understand that standardization does not make the data normally distributed. If the data is highly skewed before, it will remain highly skewed after. In those cases, it is better to apply log transformation. That is a technique we are going to see later. As shown in the figure, standardization only changes the scale and the point of reference. On the left, we see the original data. On the right, we see the same data after applying standardization. The key idea here is that the shape does not change, but now the data is centered around 0 and value represent how far they are from the mean. In this example, we apply standardization using scikit-learn. We create a standard scalar object and use fit transform to compute the mean and standard deviation and transform the data. Then we print the original data and its mean. Finally, we show the standardized values, which are now centered around 0 and represent how far each value is from the mean.
Now let's move on to robust scaling, which is designed exactly for situations like what we just saw. Instead of using the mean and the max, robust scaling uses the median and the IQR. the interquartile range, which is the distance between the 25th and 75th percentiles. The formula is x prime equals x minus the median divided by the IQR. Because the median and IQR are not affected by extreme values, this method gives much more reliable results when your data has outliers that you cannot remove. Let's see it in the code. It's the same idea. First, we create a robust scalar and call fit transform. Then we print the median and IQR so we can see what it's working with. The median of our data is 600 and the IQR is 1825. Looking at the output, 100 becomes about minus 0.27, 200 becomes about minus 0.22, 1000 becomes about 0.22, and 5000 becomes 2.41. Comparing this to what we got with normalization, the first three values are now much more spread out and readable. The outlier, 5000, is still large, but it's no longer crushing everything else.
And finally, we are going to see log transformation. The log transform is used when a variable has a very uneven distribution. This means that most values are small, but there are a few very large. This is common in data such as income, prices, or population. To apply this transformation, we use the log of the value. If all values are positive, we use log of x. If the data includes 0, we add 1 to all values to apply the log, since the log of 0 is not defined. By applying the log, large values are compressed and the distribution becomes more balanced and easier to manipulate it. However, it has some limitations. The data must be positive, since negative values cannot be transformed directly. Also, the result of this transformation is no longer in the original scale, so values may need to convert it back using the exponential function. Now, the figure shows an example of this. On the left, the data is highly skewed, with many small values and a few very large ones. After applying log transformation, large values are compressed and the data becomes more evenly distributed. So log transformation does not just scale the data, but it changes the distribution.
In this example, we apply a log transformation using NumPy. We use lag1p function, which calculates the log of x plus 1, allowing us to handle 0 values. In general, we can use log of x when all values are positive, but in this case, we use log1p. Then, we print the original data and the transformed data. As we can see, the large values are compressed, making the data more balanced.
So how do we decide which one to use? Here's a quick guide. We use normalization when we need a fixed range like 0 to 1 and our data has no extreme outliers. We use standardization, which my colleague covered, as our safest and default for symmetric data. We use robust scaling when our dataset has outliers that we cannot remove. And we use log transform when the variable is heavily uneven or spans many orders of magnitude. With this, we can wrap up our presentation. Thank you for joining us and have a great day.